All right. Good. Let me continue where I left yesterday, and I guess you must be tired by now. So we were starting to describe the dynamics of the min system to some degree of accuracy, which represents the molecular interactions in the reaction diffusion dynamics of the min system. And I here just recapitulated what I had on the board yesterday. So if you follow me through, this is the reaction scheme with attachment, recruitment of min D, recruitment of min E, and then finally hydrolysis of min E and min D. And that as a whole gives a reaction cycle which shuffles proteins from the membrane to the cytosol and back by a process that breaks detailed balance. The equations look a bit cumbersome at first, but they're not really complicated. So what you have here is, actually I didn't write down all the equations, I forgot one. So we also have here an equation for min E. Okay, so you have all these different equations characterizing the dynamics, where these equations are such that you have diffusion in the cytosol and on the membrane, and then you also have reaction terms. And as I just explained, those reaction terms come from this biomolecular reaction network, and they are summarized here. So here's attachment of min D, here's attachment of min E, and this is detachment. And we left off with a little puzzle in terms of how does that conserve mass. And let me write down which quantities really conserve the mass. So here we go, mass conservation. And this mass conservation concerns the two protein species separately. So in total, you have one species that's min D, the other species is min E, and they can be in different conformations. As you see, min D can be in the cytosol, it may be on the membrane, it's in a heterodimeric form. So if you add this up, then the concentration of min D, which is in general a function of space and time, and all the variables I'll write down here as well. So that's comprised of the cytosolic density of min D plus the membrane concentration of min D as a monomer, and then the membrane concentration of min D as a heterodimer. And now when you look at the equations, it's exactly the first three here. On those first three equations, what you have to have is that the reaction terms cancel each other, so it's that you have 0, and indeed that's the case. So the yellow terms cancel, the orange terms cancel, and the red terms cancel. So that means the quantity, which is the overall density of those proteins defined as the spatial integral of them over the whole domain, this is a constant of motion of the dynamics. So these two terms cancel. No, that's what I said. So listen. So these three terms here, they are giving, summed up, the total density of min D. And that's what I said wrong last time when we ended off. And for those three terms, you have to have cancellation, since that mass is conserved. Now there's a second species, which is the min E species. And as you can see, this has two different conformations or states. One state is in the cytosol, and the other state is as a heterodimer on the membrane. So you have here CE plus the membrane conformation, a membrane density of the heterodimer. And now you look at these two equations, And here we go. As you go to the right-hand side, those two terms cancel, and these two terms cancel. So you also have conservation of the total mass of the component, which is the min E species. All right. Now the central idea, which I tried to convey to you in the first lectures, is that the central variables you have to worry about is those protein masses. And that means if we now want to understand the system, the space we should look at is the space in which I take the protein masses as my dynamic variables. So here I have NE, and here I have ND, and I call this space the control space, and I want to map back all the dynamics on that control space, on the dynamics of the mass variables. There's one particular point, as you can see. So this ND bar and NE bar is the overall masses in the system, and that defines here a particular point in that space. And whatever happens with dynamics as I integrate over all the points in space, this has to remain, so to say, a center of mass of the dynamics. Now, how do I understand the dynamics here, right? How do I do that? Well, as I try to explain for the two-component model, the central idea is to look at the equilibria. So the local equilibria they are given by the condition that all the reaction terms here are actually canceling each other separately. So if I write my equation in a more formal form, so if I write the equation as dtu, which is just comprising all the different variables, so u includes md, mde, cd, and c as a vector. So ddu is then a diagonal tensor for the diffusion constants times the diffusion term plus all the various reaction terms, which are the terms, the vectors of the right-hand side here on this equation. Well, the condition for equilibrium simply is I have those equilibria, and they are, and that's important, they are functions of the number density of min proteins of the two species, so in ND and NNE, and they are given by the conditions that all the reaction terms are 0, so each one individually, and that I'm on the respective reactive phase spaces. So that means that the various equilibria, they sum up to these total densities. So I'm just having here ND is CD star plus MD star plus MDE star, and this here is CE star plus MDE star. So once you have that, you know that on this control space there will be a, well, quote, quote, landscape of equilibria, not in the sense that this is a free energy landscape, but that landscape just defines the location of these equilibria in the control space. Okay, so let me call this the surface of equilibria on the control space N, E, N, D. Well, and that has to be calculated by using these conditions and by, of course, choosing a proper set of these reaction rates. Well, and I can't do this, by hand, so I have to show you that by a slide. So here we go. Those are the two null-Klein surfaces or null-Klein landscapes, both plotted, as you can see, over the respective control spaces. And the way I drew it is that the average mass here for min E and min D is just right at the center of this plot. And as you can see, there's a characteristic difference between the two. The null-Klein surface for the dynamics of min E is rather boring. It's something which just goes downhill. And that has essentially to do with the fact that the reactions concerning the species min E are actually very simple, namely just this term here and the off term there. Yeah? No, this is here you have the control space variables, NE and D, and I'm plotting here the value here of the equilibrium for the min D species in the cytosol. And you're right in a sense that for each of the species, you have a separate surface. So there's a surface for the equilibrium of the min D concentration in the cytosol. There's a surface for the min E concentration in the cytosol. And there's two other surfaces I'm not showing you, which are the surfaces for the two membrane components. Right? Yeah, those are the four surfaces you have. And if you want to have this plotted in a higher dimension, I can't. This is, I guess the, yeah, no, this is not my artwork. Actually, Fridtjof, who is sitting here, is responsible for that. I couldn't do this. So this is the landscape of the equilibria. And the point is that that's guiding what's happening with the pattern forming dynamics. So you need to look at what's going on in that control space and what are the corresponding equilibria in this particular control space. Well, you ask me why and how. Well, let me first make one note. One is that if you look at those surfaces and you do the math, all these equilibria that you see here are locally stable. Again, meaning I have a small compartment and I do some small perturbation. Diffusion is really, really fast. They're all stable. No. This is for a set of kinetic coefficients, which is typical for the min system, and those coefficients, they have been derived by comparing with experimental data. Okay, so they're all just locally stable equilibria. That's one point. Yeah, go ahead. Correct. So these are two conditions actually. So there are four conditions in total and four variables. Work it out. Yeah, okay. So so the first comment is these equilibria are locally stable. The second comment is you could actually measure that. Right, in principle, measuring those is very hard. But in principle, you could set up an experiment where you would say, well, let's just do some microfluidics and be careful enough. Of course, that's a challenge. and adjust the corresponding local concentrations, make sure that the system is small enough so that it's well mixed, and then by some means really measure what the local equilibrium will be in that case. So in principle, you could actually map out those surfaces. They are, I would say, experimentally accessible variables. And they're also, and that's nice, they are the main objects for the theory. If I use those surfaces, I can tell you what kind of pattern formation you have in the system. Yeah, yeah, for sure. In a way, right? Yeah, yeah. There's some fitting problem involved. In principle, it would. Yeah. But I find this, and I've suggested that to colleagues, a nicer way of actually getting direct access, not to this reaction scheme, which is nice to know, but actually to those geometric objects that determine pattern formation. All right. Now, how do we go from there? Well, you go from there by mapping the dynamics onto the control space. So by studying the dynamics in this range of variables. And in a way, if you like, taking your language, you could adiabatically eliminate the approach to the chemical equilibria and then do a reduced description in those variables which are the conserved variables. And I've talked about this in previous lectures. So all right, so let me wipe the board and leave this for now. I don't need this anymore. So we focus now on dynamics of the redistribution of the protein mass. So what we write is dTn d, and as you sum all those equations up, because there's mass conservation, all you're remaining with is just the various diffusion terms. So you have diffusion for the cytosolic min d, you have diffusion for the monomeric min d on the membrane, and you have diffusion for the heterodimeric min dE on the membrane, and similarly just for the min E component, diffusion of it in the cytosol, and here also the diffusion constant times the Laplacian of the concentration for the heterodimers. And the logic is, as I explained it before, so you do have certain spatial gradients in all these different variables on the right-hand side. They drive the redistribution of mass. As you redistribute the mass, you're moving around in those landscapes. These landscapes are scaffolds, so they pull you up and down. And as they pull you up and down, you change those gradients here, and that affects back the dynamics of the mass. And you can simulate that, and if you do, you get the right dynamics. Now let me do simplifications in order to illustrate the key concept. So what I will do is I'll go to a simpler geometry, and the simpler geometry is one where I replace the cell by just two zones. So what we will do is, instead of taking the whole cell as an entity, I'll say I divide it up into two pieces, which I call a polar zone plus and minus. And I will write an equation which just refers to those polar zones. So what I define is a density of any of the two components, either in the right or in the left polar zone. And since I take such a symmetric case for illustration, these total densities in the right or left polar zone, they will be the average density I'm starting from, plus or minus some deviation, plus some delta. And I call the deviation the displacement from the original steady state by nu with the corresponding indices. So here you have the globally conserved variables plus the corresponding deviations. Well, once you do that, you can reduce those equations by equations where instead of diffusion along a spatial domain, what you have instead is exchange of particles between two compartments. And the exchange of particles between the two compartments is then expressed by all these different diffusion constants, which then go into exchange rates. And essentially what you have, and I don't write here the corresponding factors of pi to focus on the important aspects, those exchange rates, they will scale as the diffusion constants divided by the length scale of my domain. Well, once I have that, I can replace these equations here by corresponding equations for the two polar zones. So what I then have after some simple algebra is a dynamics for the displacements from the original homogeneous state, which is then given by not the diffusion constants, but by the corresponding exchange rates. And what comes in here is quantities that I call delta CD star, and let me define them here on the right-hand side. Those are the deviations of the chemical equilibria between the two compartments. So for the membrane, for the cytosolic component of min D, this delta is just defined as the difference of the concentration in the right polar zone minus the corresponding concentration in the left polar zone, right? So imagine just being here at a particular point, then the difference is you take this value and the mirror image, point mirror image on the other side. That defines the difference in the chemical equilibria. And I did something else here, so I put the star. If I would be correct at this moment in time, I should not write a star at first, because those equations here contain the actual concentrations of these proteins. And what I did for two components, I also do here. I say that the system adiabatically is following the chemical equilibria, so I replace the actual values by the corresponding values right at the surface of those chemical equilibria. Well, this goes on now. You have then minus exchange rate for the components min D on the membrane, and also for the component of the MDE, min DE dimer on the membrane. And those quantities, I don't write them here explicitly, they're defined in a very straightforward way. Yeah. Oh, I confused it. Thanks for asking. I mixed it up. So this, you're right. This is nu D and that one is nu E. Right. Thanks. Other questions? All right. So the quantities here are defined in a similar way. So delta M D dot dot dot. That's defined in a identical way. And here we have this equation, which is the gradient in chemical equilibria for the min E species in the cytosol and the gradient of the heterodimers. All right. So that's quite a simplification already, because instead of partial differential equations, what I have here are just two ODEs. It's an ODE for this quantity and an ODE for that quantity. So I'm actually have achieved a reduction of the whole dynamics into the control space. So into the space you see here. So these new E's and new D's, they are the deviations here from both of those center points. All right? And then you can read off what's actually happening. And the easiest way of reading off what's happening in dynamics is simply by finding the null clines. So those points in this control space where the right-hand side is identical to 0. They define those points where the system is in equilibrium. All right, how do I do this? I just have two functions, and let me do a further simplification for illustration purposes, and also because that's the right limit. So let's take those terms here, right, and account for the fact that the diffusion constants on the membrane are slow. This is 0.01, as I said, micrometer squared per second. This is 10 micrometer squared per second. So I'm assuming that the relevant dynamics is driven by just the gradients in the chemical equilibria for min D and the gradients in min E. So how would I get this then from this here? Well, what you have to do is, this is 0 if you find the points on the surface where you have mirror images. So where C at some point is equal to C at the point mirror image point. And that's something you can construct. So let's take this surface, and again credits to Fritjof. Now you add to that surface just the mirror image of that, the point mirror image, and then you see those two surfaces, they are at equal height at a curve like so, right? And what's important here is, because of the hump shape of the landscape of null clines, you get this N shape for the null cline of mass redistribution. And N-shaped null clines are really crucial and key in all of nonlinear dynamics when you study phase space flow of two component systems. All right, now let's do the same construction for this one here. And I guess now you could even fathom what's coming out. You make the mirror image, and that's going to be boring, right? This is more or less just a straight line. So I can find what's going on in my system by plotting those two null clines into my control space. So let me go back to control space. Here we are. So dynamics in control space can now be plotted. So take my notes. So I'm plotting here on the horizontal axis NE, and here, on the vertical here on the horizontal axis ND, and so it runs here nu D from 0 to ND bar and to minus ND bar and here nu E from minus NE bar to plus NE bar, right? That's the whole space you have available. And now let me plot the corresponding null clients. The one for min E is essentially a straight line, so let me draw a straight line here. And the corresponding one for the min E is this null line, which is n-shaped. So if I'm doing it right, this is roughly how it looks like. Okay, so you have this N shape, and now you can do the math, or you can just look at those pictures here, and from the pictures infer the flow. You know that the flow on the null clients has to be horizontal for the min E. It has to be vertical here for the min D. And then if you just compare where you're higher and where you're lower, you can draw in the arrows, and the arrows are here such that this flow goes like so. This one goes down, this goes to the right and up, and this also goes up. And this point in the middle, as indicated here, is unstable. And the flow is bounded because you have mass conservation. There's no way of getting out of the box. And now you take a famous theorem from non dynamics, which is the Bendixson theorem, which says if you have an unstable fixed point in the middle and some bounding box, you're bound to have a limit cycle. So you're done. Just by a very topology of what you just see, you know that the system is going to oscillate. It cannot but do that. So the oscillation will then be, well, I'm not drawing this well, but it's going to be some kind of limit cycle in the control space. Because this one is unstable. So it could be a center, but then you need this one to be, yeah, so, yeah. And what you're asking is something which is structurally totally unstable. So this is the generic case you get. So in summary, what you find is, if you take those two things together, is you could actually measure those surfaces. And if those surfaces look something like that, you are bound to have a limit cycle by just the very geometry of the problem. So min must oscillate back and forth between the two cell poles. Of course, there is ways of changing that, right? So if you now start playing with the reaction rates, you could change those surfaces. They could be changing such that you no longer have this kind of phase portrait in the control space. Then you could have bistability, monostability, and things like that. And one variable which really has, or variables which have really dramatic influence on dynamics, is actually diffusion constants. So as you can see here, if you change the values of the diffusion constants, you change how the various null-client surfaces contribute to the right-hand side. So you weigh how much weight you give to the blue surface, to the red surface, and to the other two surfaces, which I didn't show. And by changing the weight, you can actually change quite a bit what kind of dynamics you get out of it. And in general, for phase portraits in 2 dimensions, all you can kind of get is limit cycles, excitability, bistability, and monostability. Okay. Now, one case is actually illuminating. It's not one which is realized experimentally, but it's one case which I hope gives you some intuition of what's going on with the min system and what the role is of the various variables. So imagine that you, by hand, change the diffusion constant such that you make the dynamics of min E very, very slow. So you slow down this variable here, the min E variable. And compared to that, you make the dynamics of the min D very, very fast. So what's happening then in this space? So the dynamics along the D axis is fast. So that means if you start, yeah. Yeah, that's what I mean. So the diffusion constants are my measures of the dynamics, and I just say that the diffusion constant of min D is by fiat, I make it much, much larger than the diffusion constant of the min E. No, no, no. No, this is just for illustration. This is not what happens actually, because those two constants are pretty much the same. But as for the stories which you tell when you discuss a relaxation oscillator, it's just useful and instructive to make an asymptotic limit to kind of reveal what's going on. And that's what I'm doing here as well. So I, as a Gedanken experiment on the board, I assume that this is small compared to that. And that means if I look at the dynamics here, I have a fast dynamics of min D, and I have a slow dynamics of min E. So let's say I'm starting here, and you see where the flow goes. The flow is in this direction. The min D dynamics is actually fast, so those arrows here are not pointing up, they're actually pointing this way. So you pulled towards this null line here. And then you're overshooting, and once you're on that null line, the right-hand side is 0. So this is going to be slow because you are at the null line, and then the dynamics of the min E can kick in, because it's then set on the same time scale, and that will drag you up this arrow. So we'll follow up this arrow here until you're up there, and up there you're in the wind of the flow, which carries you over on the other side. So as soon as you start deviating it from this point here to the order 1, you're going to be pulled over to the other side. You go through, and same thing starts. You dragged along this null line, and then you going back. And here we are. You have now a limit cycle, which is fully determined by the shape of the null lines. And this also tells you what the physics is of the dynamics. So here on that particular point, so up here on the hill, you see that both min D and min E are positive, so they are in sync. And if I'm plotting here a cartoon of my cell with the two polar zones, then this means that now on this point here, I do have both of them, so min D and min E on the same side. Now once you're getting over that, this polarization of min D is actually unstable, and you are pulled over to the other side. So this polar profile, which has a maximum of min D on the right-hand side, is unstable. You pulled over there, and now on this side of your system, the min D has run away, and you have here the min D already on the new pole, while the min E is lagging back. So it's lagging back for a moment, but then as you crawl along the null line, they are down there in sync again. So D and E are both on the left-hand side. And again, there's a catastrophic event where this polar profile gets unstable, and you're pulled over to the other side, where now on that side you have the min D running ahead again and the min E lagging back. So that means the interpretation of what a min oscillation in essence is that the min D itself is, like in my two-component system, a dynamics which creates a polar profile. That's the module min D. The module min E is destabilizing this polar profile. In this limiting case here, it's a catastrophic event, so that this profile is no longer stable, and you're then bound to branch over to the other branch of the nullcline where you have a polar profile in the other direction. So in summary, what you can say is, if you look at the min dynamics, and that's how it should really look like if you draw it properly. This is my very short story and summary of the min oscillation. So based on all the geometry we did and based on all the analysis, this is my two-sentence summary of what min oscillations are. It's a polarity module of min D combined with a control module of min E. And I find those statements very useful also in the context of a biological system, because they give you a handle on what the role of those reaction networks really are. And what was important here is not that you have this particular reaction network, but the effect of the reaction network on the nullclines of min D and min E. Here, the reason for this being a polarity module is the N-shaped nullcline, and here the reason for this being a control module is that it's essentially a straight nullcline. And that's the elements you need to combine. So you have a geometric interpretation of the pattern formation and not an interpretation in terms of reaction modules. And so you're replacing geometry as a new way of thinking about it instead of reaction networks you could think of. Okay, so how am I doing with time? I have till 20, right? Okay, yeah. So the min system is a spatial oscillator, and I would say an oscillator of equilibria. And now let me just flash by, and this is going to be short, of things I leave out, because at this point I leave the ground of things where I can talk about it on the board, and it's getting much more technical, but I still wanted to let you know what you can do with all these methods and how you can apply this to more sophisticated real-world problems. So one question I did leave out totally was, what's the role of cell geometry? So what does it matter that you have a sphere or a cylinder, how large it is, how wide it is, etc.? And it matters. It matters a lot. So there is an issue, and we talked about this shortly, that you couple the cell boundary, which is the membrane, with the bulk, and this cell boundary coupling affects the pattern you get. So in a sense, you can see, quote, quote, the shape of a cell in its pattern as it evolves. And if you want to read about this, these are those two papers. Then there's another question. I have taken a very particular reaction network, and if you talk to biochemists, they will tell you there's more to that, of course. There is also min E, which can make conformational changes. It can go open up and close, and there's various conformations of min D, etc., etc. And here in this paper, we discuss the role of a fast switch. So coming back, that's why I asked the question in John's lecture. Here in this paper, we consider the fact that min E is a fast conformational switch, which happens on a time scale which is orders of magnitude smaller than the oscillation time scale of the min dynamics. The oscillation time scale is minutes, and the switch happens on 10 to the minus 3 seconds or something like that. And you cannot adiabatically eliminate that. That's not possible, and the reason is that it's a spatial problem, and this spatial problem develops then reactive layers on the surface, and because you have those reactive layers and the cycling dynamics, this actually matters. So it's a counterexample of adiabatic elimination, where the robustness of the min network really depends on the fact that you have that fast switch. It takes too long to explain that. I'm happy to chat over dinner. And then finally, we had a paper on also in vitro min dynamics. And that's actually the paper which started all the thinking about geometrization of reaction diffusion dynamics. And I just want to show you that. This was the motivation. So Petra Schwille in her group, Martin Lohse, they did experiments where they hijacked the min proteins, took them out of an E. coli cell, and put them on what's called a subsupported membrane. So here underneath, you have a membrane layer, and the patterns you see here, they are imaged from this membrane layer. On top of that membrane layer, you have cytosolic volume, which is actually rather high. It's of the order of, say, even millimeters, or at least a few hundred micrometers. So it's far off from anything you have for an actual E. coli cell. And what they see is this. Yep. Yeah. That's still true. That's still true. Yeah, it's 1 plus 2. Okay. And it's important. So you cannot, and that's really key here, not integrate out the z-axis. You have to worry about what's going on, not just the dynamics you see on the surface, which is beautiful, it gives these spiral patterns. You have to worry about what's going on here in the vertical direction, because there are these gradients coming from diffusion from a source degradation type of dynamics. So now the point is, you can understand those patterns in very much the same way as I explained to you. You can understand the simple patterns in the in vitro system or for the two-component system. So it's the same idea. Well, this just shows you that we can reproduce the same thing with simulations. And now what we did in order to understand what's going on, we reduced dimensionality, going from 2 plus 1 dimension to 1 plus 1 dimension. So a membrane line and a z-axis. And then we asked ourselves, what happens in those systems as you change the control parameter, which is the height of the cytosolic volume? And the way you should think of this is the height of the cytosolic volume somehow tunes how strongly you attach towards the membrane as the reservoir is kind of large or small. That's a very intuitive way of thinking about it. And now we analyzed the system, and that got us started also in this control space. The same idea as before. You have here the control space, now not plotted as the min E number and min D number, but what we plot here is the total protein concentration min D and min E, and the ratio of min E and min D. And then you ask the same question, what are the equilibria in that control space? And there's a catch now, which makes it much more interesting than the in vivo oscillations. The catch is, now you have this gray lobe, and this gray lobe is a band where you have local unstable equilibria. So if your system would move in there, it's actually driven away from the equilibrium. And to be precise, those are actually oscillatory unstable points here in that domain. So now let's go about the same way. Try to understand the pattern forming process by what's going on in control space. So I hope you got the idea from what I said previously. You map all those points in control space into the pattern by thinking of the pattern as a bunch of patches or compartments, and each compartment here corresponds to a spot on the control space. And you see the pattern here already is some initially perturbed pattern. It's no longer a flat pattern, and that reflects itself by a cloud that you see in control space. So you spatially perturb with some small or large noise amplitude the initial homogeneous state. Well, the parameters here are chosen such that this state, the homogeneous state, is Turing unstable. Okay, so guess what will happen? The system is unstable, so it will develop amplitudes. It will have some modulation in the amplitudes of the pattern, but the amplitude in the pattern then redistributes the mass, so this cloud here will blow up. And now let's watch. So here we go. The system is Turing unstable. It blows up. And at first, it looks like a nice Turing pattern with some well-defined wavelength. But because of the Turing instability, the system is moving in the regime of oscillatory instability. And once it's there, it has local pacemakers. At all these points, the system is, as you can see, creating these local pacemakers. And those local pacemakers, they then move as solitary waves through the system. And those solitary waves, they create a mess. And you can see this in both representations. So here this is a pattern. And the pattern is kind of turbulent. You can measure that by various means. Just means there's a lot of wavelengths and timescales in there. But you can also see that the attractor in control space, which is my main geometric object to characterize what's going on, is also a fuzzy object reflecting the turbulent behavior in the actual pattern. You have a question? Genau. This here is just a state is the amplitude of the min d density. You should choose one of the various densities. Which one?
So a state is the distance from the chemical.
Oh yeah, okay.
Before we had everything slaved in.
Yeah.
Now you actually see that when you enter the locally unstable region, you're blown away from
Yeah.
zero, from your what the bench used to define distance. Is some Euclidean distance in concentration space.
So if you think of those surfaces, which we had in the previous slides, is the distance from those surfaces.
Because Euclidean distance usually weights the different components equally.
Okay. What's funny about that, and I stop here actually because I don't want to go too deep into that. The funny thing about this observation is that that turbulent state happens at onset. So if you think of a band of unstable modes emerging here in this type of system, the observations where you see the turbulent state happen right at onset. And that's funny because that's not what you usually have. You usually have close to onset some nice pattern, and only if you drive the system hard enough, you get then turbulent behavior. Here it's the opposite, and I'll leave you with that because I guess this takes me too far out of the scope of what I want to talk about. Sure, go ahead.
So this seemed to come about because that Turing pattern you created had a quite large amplitude. Why did the Turing pattern have a large amplitude just at threshold? Why didn't it?
Good question, very good question. So I asked back, second order phase transitions are characterized by what? If you go through the bifurcation, the order parameter is small. Those, yeah. Right. So there's nothing holding you back. So if you fine tune the system to a supercritical point, you can kind of, keep the Turing instability in check and not grow it, grow large. So you remain here in this regime and you're fine. But generically you don't, because those transitions are subcritical. So as soon as you hit the transition, the amplitude is of order 1, and that gets you into those regimes. Yeah. So the whole story, the whole talk, and interesting enough, if you move closer to that point, you get regular patterns. And those regular patterns, they are the spiral waves which have been observed in the experiment by Lohse and Schwille. And the reason is there's a commensurate, incommensurate type of phase transition happening, and so on and so forth. It's a long, long story, and I find a very beautiful one. The point I want to make here is simply, I really strongly believe that this representation in terms of control space is the way of representing these patterns and gain insight into the dynamics, because that here is very hard to interpret. This is easier to interpret in terms of geometric concepts that you have available in the system. All right. So that kind of closes my story on pattern formation, and I also wanted to add another topic, since I still have this lecture and tomorrow's lecture. And what I wanted to add on is a discussion of another type of active system, which hasn't been talked about yet, namely an active system where you have molecular motors moving along microtubules or molecular motors walking along actin filaments. It's an active system in the sense that you have motors. They are self-propelled particles. It's different from the systems you saw because the motors have a very strict sense of direction. They go straight. Okay, so let me also go through that with a few slides, and I'll put them online. Just not able to draw these pictures. That's fine. Okay, so this is a story. This is a microtubule. How many of you know what microtubules are? Okay, most of you. Okay, so that's a microtubule, and there is motors that run on microtubules, and this is the cartoon you see on the internet, where you have these nice kinesin motors driven by ATP hydrolysis moving along the backbone of such a tubular highway. And typically you say they're going straight, but they don't have to. There's different motors. They're called kinesin 1 and kinesin 2. Kinesin 1 goes straight, and kinesin 2 actually goes like so. And let me see where I have that. So here we go. This is how you measure it. That's 2 optical tweezers. You clamp a microtubule in there. You watch the motors move. And here are different motors. They have different names. And what you should notice is that they're actually running in circles. And here it is. So here's another picture which visualizes how they run in circles. Now what I want to analyze tomorrow essentially is what happens if you have on a tubular highway motors moving straight and another set of motors moving in a spiraling fashion against them. It's like asking you having 2 pedestrians crowds walking along a road. One is going this way, the other is going that way. What will happen? And the story will be that you get nice non-equilibrium phase transition, including a jamming transition. All right? Yeah? The microtubule you can't see, I think. As you have something on it which they carry along, which is huge, in order to make it measurable, right? So this is not supposed to scale in any way, right? So the typical pitch of such microtubules have a diameter of something like 10 nanometers, and the motors, they walk here with a helical pitch which is roughly something like 20 or 30 nanometers. And this is just to visualize in terms of putting some beads or something else on it. All right, so I'll leave you with that motivation. And now let's go to the board and start with the basic discussion. So this basic discussion talks about lattice gas models, and one of the really key representatives of that, the totally asymmetric simple exclusion process. And again, how many of you know that process? Okay, almost all, but not everybody. Well, so today I'll introduce lattice gas models. And we had that, so think of your system as just some one-dimensional lattice or some two-dimensional lattice. And then on that lattice, you can define here the number of individuals on that site. You can also define the type of individual on that site. So for example, you could have here on one side just a single motor, or two or three, or you could have one motor of one type and another motor of a second type. And that's of course important because it determines whether I have exclusion or I don't. And then you have to define what kind of dynamics you want to incorporate in such a lattice gas model. For the example you just saw of these motors walking along microtubules, it's essentially a Poisson process which moves forward with a fixed rate nu. And essentially there's no backstep of those motors, it's very minor. And on those lattices you might have also some processes which are hopping forward, but you could also have something which does diffusion and other types of transport processes. So you specify how you move on the lattice. In addition of that, you also specify some other sets of rules which you also can call reactions. So say you have two species on the lattice, call them A and B. Later there will be maybe two different types of motors. And I had this on the board for the diffusion reaction system. That could be an infection process such that you transform a B into an A. Those rules could also be of a more sophisticated type, namely, so this is another example. You could have three species interacting with each other, A with B, B with C, and C with A. And you could define this such that A wins over B, B wins over C, and then C back dominates on A. And that's just the rules of a well-known game, namely rock, paper, scissors. And there's more complicated games, and we actually studied those, motivated by some show which you all might know, namely Big Bang Theory. There's rock, paper, scissors, lizard, Spock, which you can also study. It's actually quite fun. So what you have then is configurations in the system, and those configurations, C, they define just the overall state of the system. So C equals the configuration of the system. That means you specify the number and type of particles at each lattice site. Okay, once you've done that, you can in principle write down an equation for that, which is called a master equation. So you study what's the time evolution of the probability density for a particular configuration. And in general, this is just a set of rules telling you when you gain or lose probability density by all these different processes like hopping, random walks, or chemical dynamics. How you deal with that is actually quite a difficult problem, but there is a nice way of actually linking different types of mathematical descriptions, and there are three which I think are the most prominent ones. You can have a master equation which is of the structure I just wrote. You can actually rewrite the master equation also in terms of what's called a generating function. Then you get a partial differential equation for the generating function, and you can use that differential equation for the generating function to construct a path integral. I'll not go into that, but what I wanted to mention is that together with a student we wrote a review article where we describe how you go from these different descriptions without using the language of quantum mechanics. So for those of you who know, the way you can go from a master equation to a path integral description, often the concept of coherent states and Fock space formulation is invoked. You don't need that. You can actually stay fully within a purely stochastic description and go between all these various descriptions. So if you want to read, this is Weber, and it's in reports on progress in physics in 2017. What I will do is much simpler than that. I will formulate this process which you just saw, namely the dynamics of a bunch of particles on a lattice in terms of a mean field theory, and check how that mean field theory is actually valid or has to be modified. All right, so what we look at is a simple model for transport called the totally asymmetric simple exclusion process. Or simply TASEP. This of course goes back to work by Derrida, by Joachim Krug, Gunther Schütz, and many others, and actually its original formulation was in a paper in a biological journal by MacDonald. So the idea of the model is to represent in a simple way interstellar transport. So what we have is a lattice corresponding to a dimer on a microtubule. So you go from 1 through L. That's the microtubule lattice. And then you simplify a molecular motor by a monomer, which is not correct, but let's just assume this for a moment. So let's take this here to be a molecular motor and say that this hops forward at a certain rate nu. And the conditions here are such that if a lattice side and its neighboring lattice side in front of it are occupied, then a jump like so is actually forbidden, and that's called steric hindrance. And this is simply due to the fact that these molecular motors can just individually bind with their heads on the molecular tracks and therefore cannot be double occupied. Now those microtubules are embedded in some cytosolic volume. So here there is, say, some reservoir, and there as well. And the way you model that is to say that there is a rate by which you fill the first site, which is called alpha, and a rate by which you empty the last side, which is called beta. And that's it. That defines the totally asymmetric simple exclusion process. And it has been quite a range of theoretical methods that have been applied to that, which are very sophisticated. But I would say the most important things for us now, you can actually understand quite simply in terms of a mean field theory. So what you do is you try to encode this here in terms of a stochastic description. So let's say I introduce occupation numbers, which are either 1 or 0, depending on whether the site you are located at is occupied or not. So 0 means empty site, and 1 means a occupied site. Then if you put yourself at a particular position, and let's call this site here mu. So you look at a site mu, and you ask yourself, how is the update of this particular site in a small time interval dt? So update in a time interval between t and t plus delta t. Right, so there's two things that can happen. If you're at a particular site, the particle you choose may try to hop forward or it may not. It tries to hop forward with a probability nu times delta t. There is an attempted hop forward, and the way you can describe that in a very shorthand way is to say that n mu goes to n mu prime with that probability, and now I write n mu prime such that I encode in the expression that I have here the fact that there is exclusion between the different particles. Okay, so let me write it down and then show you how it works. So this is n mu plus n mu minus 1, 1 minus n mu minus n mu 1 minus n mu plus 1. Okay, let's look at cases so you see what I mean. Think of a case where you have the site mu minus 1 being occupied and the site mu being empty. That means you start from a configuration where n mu minus 1 is 0 and n mu is 1, and you end at a configuration where n mu equals 1, n mu prime is equal to 1. Oh yeah, sorry. Thanks. So here I have it's late, so 1 and 0. And now you end up with a different configuration where now n mu prime is 1 and n mu minus 1 prime is 0. Just hop forward, and you can check by comparing that this is actually right. And you can also include that term. So this one here and that one here, where you have mu and mu plus 1, and as we know, this is forbidden, and that's actually exactly taken care of by those terms here of 1 minus n mu plus 1 and 1 minus n mu. They make sure that such a process is not possible. So in this simple way, you can just encode all the different cases which otherwise you would have study piece by piece. The other process is that you don't attempt a hop well, then things are trivial, because if you don't attempt to hop, you just stay where you are. So with probability 1 minus nu dt, you just stay where you are, and n mu prime is identical to n mu. Now once you have that, you can immediately write down the equation of motion. So the equation of motion then is n mu at this later time is two options. Either you change to a new variable with probability nu dt, or you stay where you are. So you stay where you are. That just means you have the same value with a probability 1 minus nu dt, right? And now you insert the expression which I wrote down. So let me call this here star. You just insert that expression, and you form the difference n mu t plus dt minus n mu of t divided by dt. So you get d n mu of t divided by dt equals nu. Then you get two terms which are quite easy to interpret, and I'll come to that in a second. Okay, so that's what you get in the end. And you just have to read this out to understand what that means. So you have a change in the occupation number at site mu, which is gain minus loss. You gain if at the side where you are is empty, and you hop from the back side towards that side. This is the in process. And you lose if you are sitting at side mu and the side in front of you is empty and you hop forward. So it's a simple way of writing the master equation, if you like, in a form which connects, and that's the very unfortunate thing, the first moment with the second moment. So this is exact as far as it goes, but you have to, it's not closed. You have to add the second order term, meaning you have to write an equation now for the second moment, and then you'll find this is also not closed, etc. There is sophisticated ways of solving that exactly, but I won't go into that. It's not necessary, because in that case it turns out that if you simply do this, meaning you replace the correlations by averages, so you break up the moments, that this mean field theory, right? So what I'm doing here is a mean field approximation where I'm neglecting all kinds of correlation between the different sites. This approximation gives you a lot of the things right. In particular, it gives you right the phase diagram and the rough profile of the density of motors along your microtubule. And in general, it's not closed as for many other systems, and you've seen that in many other talks. There's this hierarchy problem in such kind of equations. Right, so what you can do is to go even a step further in coarsening the dynamics. So you now define a density rho mu simply by those averages. And you should read this either the density, if you like, or as the probability of finding at a site mu a particle, yeah. In addition, what I want is that I will take a hydrodynamic limit which says that on the scale of a lattice site, the profile rho mu is smooth. And if you have that, then you just look at this right-hand side. So this is r mu minus 1, 1 minus r mu, etc. And you already see that that has first and second order derivatives in it. So let's do that. Let's do a Taylor expansion of the right-hand side. So let's take position x being position times a, and a being the lattice constant, which I take equal to 1 just to simplify notation. And then as you Taylor expand here the right-hand side, you get d dt of rho and x and t equals 2. The leading order terms cancel, and then the first term you get is 2 rho minus 1 dx rho times nu. And there are higher order terms, and I'll come back to them maybe later, but for now let me just say that they are terms of the order delta x squared. So if you want to write them, you can always write them as d dx squared rho. Just need to say what d is, and d, if you do the math, turns out to be nu over 2. All right, so leaving this aside, the left-hand side already is very interesting because you can rewrite this in a form we already had in previous presentations. So you can write this as a gradient of a current, J of rho. And this current, if you again just do the simple math here, is equals the rate times rho times 1 minus rho. So in that case, if you look at this as velocity times density, the density is actually here appearing in the velocity, slowing it down as you increase the density. So if you plot that, this gives you a current density relation, J of rho, which is such that you have zero current at zero density, then you have a maximal current at a quarter, and you again have zero density at zero current at density equal to 1. Yep, so all right, because I have a time scale and I can pick that time scale. And that's essentially how far I wanted to go for today, because that's just standard knowledge, and there's a wonderful review article by Richard Blythe and Martin Evans, which really summarizes this in a nice way, and essentially have stolen the notes you just see from this review article. The point I want to make is, for this particular system, you can go through a coarse graining procedure with a master equation. You break it up by mean field, And then you end up with a mesoscopic equation. This mesoscopic equation has the form of a conservation law with a current that has a funny form, namely that it's increasing first and then decreasing as you increase the density. And as a consequence of this current density relation, you can show that that system has different types of phases. One phase where you have a low density, one phase where you have a very high density, and the third phase where you have a maximal current. Or say it differently, there's one phase which is determined by the entrance current, so by alpha, which is the bottleneck determining the current in the system. There's another phase where you put here a red light. Then beta, the exit rate, is dominating the behavior. That's the high density phase. And the third phase is one where the system doesn't care about the boundaries. And then it's in the maximal current phase where the current is given by the maximal value here at density of a half. Yeah, and I'll summarize this tomorrow. I guess for today it's a bit much to add this as well. Just wanted to make the point. This here is mean field in its strongest form, despite the fact this works beautifully well. For the case I'll discuss tomorrow, where you have one particle current going this way and the other one going that way on a cylinder, you'll see that this mean field theory actually breaks down, and there are interesting correlation effects because of that, and those correlation effects give rise to a new type of phase transition in those 1D systems, which is a jamming transition. Okay, so far for today, and if you still have questions, you may ask them, but we may also go down for dinner now. Thanks for listening.